A heat exchanger is a piece of hardware, a solid, that separates a hot fluid, in your case the fire, from a colder fluid that needs to be heated, and that's the water in the house piping system, or whatever, or the steam in the boiler of the locomotive. So solid surface, and I'll sketch it here. That's the view in profile. In other words, the actual thing is long the other way. And above it, there's a flow of high temperature. Let me be true to my notation. Hey, my notes don't have a temperature there, but we could call it delta T, meaning that the temperature of this plate, the separating surface between hot and cold, is 0. And the setup is, the purpose of it is to transfer a heat current called the lowercase q of what earlier today it was called capital Q dot. This time is lowercase q. To this piece of hardware. Now, I said this last time, organs do not happen by themselves. They happen because they are useful in something else that's much bigger. And that much bigger is a vehicle. There are heat exchangers everywhere, from cooling the engine to providing air conditioning to the passengers. So the bigger thing is the vehicle. And this piece is something somewhere, for example here, in a motor. Meaning that what matters, you're already inside the cabin. Here's you. You're aware of the fact that your vehicle is heavy, for which you have to pay for the gasoline to move it. But it is heavy for palpable reasons. Everything is heavy, including the motor and the pieces inside of it. So this thing, the heat exchanger has a weight, which is the mass of it. The mass of it is the following: if the area of the heat exchanger is A, meaning here A, and the thickness is T, then the density times the volume times that makes the mass times G. G is gravitational acceleration, is the weight of the object. You learn very soon in this course, and it will be a small group of lucky inhabitants of the planet who know that force downward is proportional to force horizontally. And the horizontal force is the drag force experienced by any vehicle, man-made or animal. And the drag is proportional to the weight. Kind of interesting, don't you think? So if this is the weight, then this other one is some factor, sometimes, but only sometimes, equal to the friction factor. And then the weight fits in here. And why is this important? It is important because the user must pay for the movement at a particular rate. So the rate of power dissipation or power consumption horizontally, I say horizontally, forget about that. It's about the story about locomotion, is equal to this mu meaning this force, mu, and then rho ATG times the speed of movement. So that is one way in which your pocket is hit. You have to pay for changing your position on the surface of the Earth. But the other thing you pay for is the power dissipated, obviously irreversibly, by the transfer of heat from high to low. And we already know that the other penalty is I'm not sure whether this is the equal sign, but I'll put it this way. The through and across means this is the through, and the across is delta T. That's how today's lecture began. Also in convection, this is a convection setup. We have that Q is equal to HA delta T. The purpose of the heat exchanger is to vehicle a heat current across the surface. So this is required. Therefore, delta T from here is replaceable by Q over HA. So the second penalty varies in proportion with the job of the drawing divided by the size of the surface, the heat exchanger surface. And now once again, what works in this domain that I'm teaching, which is that of questioning. Questioning happens in your mind. It doesn't happen speaking or screaming in the street. You question yourself, what about it? And you see then the answer in your mind is the drawing of the total penalty to you, which is W1 plus W2. Unfortunately, it's always greater than 0. And the single degree of freedom in the drawing. And that is the size of the surface called A. A is the degree of freedom. Degree of freedom. The thickness of the surface or of the wall might be another one. But in the simplest exercise, it is fixed because you buy, sheet metal of a particular size from a catalog, and you can cut from that a small a or a big A. And well, let's see, we have a contributor that contributes a penalty, quote unquote, contributes proportional to A. That's W1. And then the other contributor does the opposite, which is a descending hyperbola. And this is a drawing just like the one I made last time, where what pains you is the sum. And that's how you discover mentally, not always the precise answer, but the existence of a trade-off between the two penalties. And that in this case happens exactly at the intersection of the asymptotes, which is here. And the formula for that, I forgot to write down. But you can we have a few minutes, I'll get it for you. Just to show you how the answer teaches a lesson, okay? So I say mu rho a t g u, the same as q. Oh, by the way, the penalty, oh yeah, there's u, the speed of the vehicle, and then h a, and that takes you to a squared, but later I'll take care of that. A will vary as q squared over h, and then downstairs mu rho tg. To power 1/2, and the capital U. See that? In other words, the size of the area for least fuel consumption should be proportional to the heat transfer rate through the surface. So if you hear from the engine maker that the heating rate or the cooling rate to the ambient should be a particular number of watts, you will know that proportional to that number should be the size of this piece of sheet metal. That's one thing. The other is that the faster the vehicle, the heat exchanger that's better is smaller. Think about it. Higher U, smaller organ of this type. This sort of surprise may be useful someday, but more useful is because now I'm talking to myself, to the camera, more useful is the thought that size matters. Size, a particular size, comes from reasoning and questioning, and the reason everything matters is because it costs money. And you heard the expression that have money will travel. To move is to be alive, according to Leonardo da Vinci. So thank you, Adrian. I remember next time I will try to start with him. Yeah. I have a kind of a funny way to think of Da Vinci. Well, it's okay, I'm about to explode. Colleagues of mine, and also these people who write the books of physics, claim that modern science began with Galileo Galilei and Newton. Yeah. Not really. Newton was born 100 years after Galileo Galilei. Galileo Galilei was born 100 years after Da Vinci. And Da Vinci, when he died, he left all these papers, meaning notebooks, in a library in Florence, which is where Galileo grew up. So, and as you'll hear next time from Da Vinci, you'll recognize the meat and bones of today's science.